After having discussed the basic symmetry elements and symmetry operations and in crystals, including the translational symmetry translations and the combined elements, which was on the program last week, today I would come to the traditional crystal chemistry part, which is the derivation of basic crystal structure types from the concept of close packing of spheres. And we mean atoms or ions under the spheres. And this close packing concept is based on the crystal, on the chemical bond, which is not directional. And this is a typical bonding scheme in metals, but also in ionic crystals. But as we'll see later, also the crystal structure types of more or less covalent or polar structures or crystals can be derived based on this close packing scheme, although the structures are more open and the bonding is more directional. That means the coordination numbers are decreased to, let's say, 4 or sometimes even lower coordination numbers. And this these crystal structure types of binary or even ternary compounds can be derived by occupying the interstitial sites in close packed structures by different type of atoms or ions. And by occupying these interstitial sites, we obtain the specific coordination numbers. And these coordination numbers of the atoms in the close packed arrays and those which fill the interstitial sites are related to stoichiometry. So I will also address this issue, the relation between the coordination numbers and stoichiometry, which refers mainly to binary compounds. And then we'll go through the different basic structure types derived on the so-called hexagonal and cubic close packing. But not all structures can be interpreted in terms of this concept of close packing. For instance, the silicates and other layered or low dimensional structures can be derived. So I will briefly mention some of these which are based rather on the linking of various types of polyhedra in 3, 2 or 1 dimensional arrays. And in the end, I would address the difference between an ideal crystal and the real crystals, which always contains defects. And the defects are of different types, but what is again a typical scope of crystal chemistry are the point defects, which are substitutional defects or vacancies or interstitial sites occupied by different atoms and so on. So this is probably the last part I'll be able to speak about today. So first, the close packing of atoms or ions. As I mentioned, it is relevant to ions or the elemental metals, where the metallic bond and the ionic bond prefers high coordination numbers. The coordination numbers in close packing are typical 12 nearest neighbors. How can we derive these close packed structures? So we can start from the close packed arrays of atoms in one layer. So if we create an array of one layer of atoms, then the second row, in order to obtain the close packed array, would be placed here. like this, and the third layer like this, and so on. And in this way we obtain the two-dimensional array of close-packed spheres like atoms or ions. And now we have two options how to lay the second layer of this. One is, let's say, the position. If this layer is denoted as A, then the second layer, in order to have a close-packed array, can be placed here, and let's denote it as B. Something like that. But then if you place an atom here, you can't, and you continue with a layer, you can't put the atom here, only here. So this is also B, B, B. But this position will be denoted as C. Okay. And so if the first layer is referred to as A, then the second, let's say we put the second layer in the B position. And now the question is where to put the third layer and continue in a three-dimensional pattern. And the so-called hexagonal close packing is based on AB pattern. So the third layer is eclipsed, yeah, with the first layer. So so we have this layer and this one one above the other. And the red one is the B layer. The color here doesn't represent different atoms, but only different positions of atoms or relative positions of the layers. So both green and red atoms belong to the same type of atom, but the color denotes the different arrangement or different position. And this pattern is hexagonal. We can clearly see that this one layer close packed structure is hexagonal because the unit cell is this one with 120 degrees angle here. So we have the two-dimensional hexagonal lattice. Indeed, the next unit cell will be this one, and the next unit cell here will be this one. But the hexagonal axis is clearly visible if we connect the points like here. We have an hexagon, okay? So this is clearly the hexagonal symmetry. And this hexagonal symmetry is retained if we continue stacking the layers in this AB pattern. So the three-dimensional unit cell looks like this one, where this atom belongs to the A layer and this one belongs to the B layer, and they are in. Can you mute your microphone, please, because it's just mute your microphone. So this atom is in 1/4. This atom is in 3/4 of the C lattice parameter. And if you look from top down, this one is in 2/3 and 1/3 as concerns the X and Y directions, and this one is in 2/3 and 1/3. But we can also move the origin of the crystal lattice to this point, and then we have this representation where the atoms are in the corners of the hexagonal unit cell, and one is in 1/2 in C direction, and again in 1/3 and 2/3 as concerns the position here in X and Y directions. And because the stacking pattern is AB and AB, then if we consider the coordination number, we have 6 atoms within the layer, the nearest neighbors, and 3 atoms above, and 3 below and 3 atoms above this atom, which is considered here in the center. So the atoms in above and below form the trigonal prism. So they are again in an eclipsed position. And the coordination number is 12 for this arrangement. And we can also calculate the so-called space filling factor, which is the ratio or fraction between the volume of atoms considered as rigid spheres and the volume of the unit cell. So here we have 2 atoms per unit cell, which is clearly visible here, but also here, if the atom is in the corner of a unit cell, then it contributes only by 1/8, because this corner has 8 nearest neighbors unit cells. So we have only 1 atom which contributes to this unit cell positions in the corner, and the second atom is completely inside the unit cell, so it contributes by 1. So there are 2 atoms, and each atom has the volume 4/3 pi and the cube of the atomic radius. And now we have to express the volume of the unit cell, which for the hexagonal unit cell is a square, but it is the shape of the unit cell imposes that we must multiply one lattice parameter by cosine of 30 degrees or by sine of 120 degrees, which can be drawn here. If you have this unit cell, then this is the parameter A, but in order to calculate the area of this, we must take this distance, which is A times sine of 120 degrees, which is this angle, or cosine of 30 degrees, which is this angle, okay, 30 degrees, times the C parameter, which is perpendicular to it. And now we can, using some goniometric relations, which are shown here, we can express the A and C parameter in terms of the atomic radius, based on the assumption that the atoms must touch, and they must the spheres must be touching here on the A edge, or here. So based on this, we have the conditions that 4 times RA must be equal to the lattice parameter A, because no, 2 times only. 2 times, because the 2 atoms must touch on this sphere. So we have 1 atom like this, and another atom like this, and this distance is 2 times RA. And for the C parameter, it is more complicated. We must take the condition that on this distance, these 2 atoms in layer A and B must touch. So here we have the 1/2 of C parameter. So we take this distance, which is 1/2 of C parameter, and then this distance, which can be calculated based on the Pythagoras law. So we obtain this relation for C parameter, that is 4 times square root of 2 times the RA and over the square root of 3. And based on it, we can express the volume of the unit cell as a function of the RA, which is again the cubed function with respect to RA. So if we divide the volume of atoms by the volume of unit cell, the RA cubed is cancelled, and we have this relation which denotes which means the filling factor or space filling factor, which is 74%. And no wonder that if we go to another arrangement, we obtain of close packing, which is the cubic close packing, we obtain the same filling factor. The difference between the hexagonal and the cubic close packing is just the sequence of the layers, which is A, B, and then we use the third position, this one, C, here, and this is the third layer, and then we repeat this sequence A, B, C. But now the symmetry of this arrangement is changed because we can express, or we can define the unit cell for this arrangement as a cubic one, which from the first glance is quite strange, but the point is that the cubic unit cell, in fact, its diagonal, the body diagonal, corresponds to the direction of sequencing the layers in this along the C parameter of the original hexagonal lattice. So perhaps you remember that there is a relation between hexagonal and rhombohedral unit cell, and the rhombohedral unit cell is a general shape for a cubic unit cell, because the rhombohedral unit cell has the same lattice parameters. The length of the lattice parameters is the same, but the angle between the lattice vectors is different from 90 degrees. But the cubic unit cell is a particular case of a rhombohedral unit cell where the alpha angle is 90 degrees. So this direction corresponds to the diagonal of a rhombohedral unit cell, but in this case, because of the close packing, it is not a rhombohedral but the cubic unit cell. And here in the cubic unit cell, this atom, which is in this corner, corresponds to the A layer. Then these 6 atoms correspond to the B layer, which is green on the left side figure. Then these 6 atoms correspond to the third layer, denoted as C or in yellow color. And this atom is again a part of the A layer here. And the cubic unit cell is face-centered. That's why we have this symbol FM3M, which is the space group of this structure. And in this case, each atom is again 12-fold coordinated. Again, 6 atoms are in the same arrangement as in a hexagonal unit cell. That means the hexagonal arrangement here. But then we have 3 atoms here and 3 atoms here. In this case, in anti-prismatic arrangement. So this atom is positioned here, and these 2 atoms are positioned here. So it is an anti-prismatic arrangement, and this cubic close packing has, or we can use 2 symbols to denote this cubic close packing, either CCP, which is directly the shortcut for cubic close packing, or FCC, which reflect the symmetry of the unit cell and the corresponding the symmetry of the translational symmetry of the unit cell, which is face-centered. That means the atoms are not only in corners, but also in the centers of all phases of the cubic unit cell. And there are 4 atoms per this unit cell. In hexagonal close packing, which is referred to as HCP, hexagonal close packing, we had 2 atoms per hexagonal unit cell, but here we have 4 atoms per cubic unit cell, because each corner contributes by 1/8. So one atom in general, one corner atom in general contributes to this unit cell, while the atoms in the centers of phases contribute by 1/2, and there are 6 these atoms. So in total 3 atoms from the phases and 1 atom from the corners, which yields 4 atoms per unit cell. And the space filling factors is exactly the same as for hexagonal close packing. Here we have 4 atoms times the volume of a single atom expressed in terms of the atomic parameter, and the volume of the unit cell is a cube. And now we use the conditions that the atoms on one phase must touch on the phase diagonal. So this and this and this atom must be touching in order to preserve the close-packed structure. And this phase diagonal is equal A times square root of 2. So we have A times square root of 2, which is the length of the phase diagonal, and this must be equal 4 times RA, because the atoms must be touching here. And we have 1, 2, 3, 4 radii, sphere radii or atomic radii along this phase diagonal. So substituting this, we obtain, we can express A is equal 4 RA over square root of 2, and 2 over square root of 2 is equal to square root of 2, so we have this form. And we obtain the same result, that the space filling factor is 74%. So these are the closest possible packing arrangement of atoms or ions, as we'll see later. But there is another one which is not as dense. It attains only 68% of the space filling, and it is the body-centered cubic packing. So we have the unit cell has the atoms in the corners, which contribute by 1/8, and the 1 atom in the center. And now the space or the close packing condition is that the atoms on the body diagonal must be touching. So we have the body diagonal, and this and this and this atom must touch along the body diagonal. So the condition is that 4A must be equal, 4RA must be equal A times square root of 3. And this results in this formula for the volume of the unit cell. We have 2 atoms per unit cell times the volume of an atom yields pi times square root of 3 over 8, which is 68%. So this is the third possible arrangement, which is frequently observed for real crystal structure of metals. If we look at the structures of metals, We have either BCC, which stands for body-centered cubic, then HCP, hexagonal close packing, and CCP, cubic close packing, also denoted as FCC, face-centered cubic. And the structures of the individual metals in their ground state or standard state, which is room temperature and normal pressure, are shown here. And you see that the vast majority of metals adopts one of these crystal structure types. The exception is manganese, which has cubic structure, but quite complex with many atoms per unit cell. And this complex structure is associated with the unpaired spins and spin-orbit coupling, which is present in manganese. So, and the mercury, which is liquid at normal temperature. In the first semester, we briefly mentioned the Engel-Brewer rules. There are two Engel-Brewer rules, and the one refers to structure, and the rule postulates that those metals which have low number of electrons available for bonding adopt the BCC structure. Then those which have intermediate number of electrons available for bonding adopt the HCP, and those with higher number of electrons CCP. But as you can see here, there are many exceptions. This is rather a trend, not a law or not a rigorous rule. We have also the BCC structures for the atoms in the center of the transition metal series. We have the hexagonal structure and cubic face-centered structures for alkaline earth metals as well. So it is just a trend only, or tendency. In some actinides we have more complex structure. The structure of uranium is orthorhombic. The structure of plutonium is monoclinic, but plutonium has 4 or 5 different structures if you increase the temperature, and at high temperatures it adopts the FCC structure. This is called so-called delta plutonium. In some cases, like for hexagonal structures, we can have more complex arrangement. For instance, americium has the structure pattern ABAC, ABAC, so the C parameter is longer compared to the basic hexagonal close packing, but still it is denoted here as HCP. It is hexagonal close packing, but more complex arrangement along the C direction of the hexagonal unit cell. Okay, so this is as concerns the metallic structures. Some intermetallic compounds can also be or adopt the structures based on close packing, or most of them in fact, but their structures are based on ordered substitutional defects. If we replace one atom by another and we arrange the atoms in a pattern, then we can obtain an intermetallic structure. So let's say for 1-to-1, let's say the intermetallic compounds which let's say has the stoichiometry Cu-Au, so the copper gold intermetallic structure with 1-to-1 arrangement, we can have a row of copper atoms and a row of gold atoms, and again Cu and Au and so on. So this is a ordered structure, also a compound, which is based on the ordering of substitutional defects, which are 1-to-1 in the stoichiometry. And now let's come to binary and more complex compounds, usually ionic or highly polar, but as I mentioned, also some covalent or weakly polar binary compounds can be derived based on occupation of the interstitial sites within the close packing. And we have two kinds of interstitial sites, in fact. In fact, there are more, but the two basic types are tetrahedral site, which is created if you put 3 atoms in one layer, and the second layer is at this position, the orange color. Then inside there is a tetrahedron. This shape is a tetrahedron, and inside there is a space for a smaller atom, which might be, for instance, a cation, and the close packing can be based on the arrangement of anions. Here in cubic close packing, we have in the unit cell 8 tetrahedral sites, and as you remember, the number of atoms in the close packed structure is 4 per this face-centered unit cell. So we have a double number of tetrahedral sites compared to the atom in close packing. So, and the tetrahedral sites form a cube inside the cubic unit cell. You see, there are 8. And in cubic close packing, we have also octahedral sites. These can be seen here. So if you consider the first layer in green color, and then the second color is positioned in orange here, or drawn in orange. Here we would have a tetrahedral site, but next to it there is an octahedral one. But now we look at the octahedron from one of the faces. So if you draw an octahedron like this, then if you look from this direction, you have 3 atoms here and 3 atoms in staggered coordination, so rotated by 60 degrees compared to the upper triangle. But in the cubic unit cell, the octahedral sites are quite simple to view. They are all on all edges, and one is in the center. You see that there are 6 atoms in an octahedral arrangement around this central atom. And in fact, the ratio between the octahedral sites and the number of atoms in the unit cell, in the close-packed array, is 1-to-1, because each edge contributes by 1/4, because there are 4 neighboring unit cells around this edge, or this edge is shared by 4 neighboring unit cells, and we have 12 atoms on all edges. So 12 over 4 is 3, and this atom is in the center. It contributes completely to this unit cell. So there are 4 atoms in octahedral positions and 4 atoms in close packing. So it is 1-to-1. And if you look at the arrangement of the octahedral of the atoms in octahedral size, which are green, they also form an FCC lattice, which is just shifted by 1/2 of the unit cell edge. So these are in fact two interpenetrating FCC structures. Each cation or atom of one type is coordinated by 6 atoms in octahedral arrangement, and also each atom in the original close-packed structure is surrounded by six atoms in octahedral positions, because if you extend this pattern, we have another green atom here, and another green atom here, and another green atom here. So again, the octahedral arrangement. Now, for hexagonal close packing, we have again the tetrahedral sites, which are 2 completely inside the unit cell and 8 on the edges, but each atom which is on the edge contributes by 1/4. So 2 atoms on the edges contribute to this unit cell, and 2 atoms are inside the unit cell, which is 4. But the number of atoms in the hexagonal close packing per a single unit cell is 2. So again, the ratio between the tetrahedral sites and the atoms in close packed arrangement is 2:1. But in this case, these 2 atoms in tetrahedral positions are very close to each other, and these 2 positions can be occupied simultaneously. Unlike the cubic close-packed structure, where all tetrahedral positions can be occupied in a single structure, it is not possible in this case, because it corresponds to 2 tetrahedral sites above each other. Let's say one is here, and you can consider this orange circle or a sphere below, and the second atom would be just below the first one, very close to each other, and the cations repel each other. So and the proximity of the 2 tetrahedral sites makes it impossible to be filled simultaneously. And here for the octahedral side, we have extended the unit cell to this hexagonal prism. In fact, only this and this atoms contribute to the unit cell here. The others are in the neighboring unit cell, but there are 3 in one layer, let's say A, and 3 in the B layer. And the octahedral position is here, and you see that this C direction corresponds to the direction of the threefold axis of this octahedron. So the octahedron around this central green atom is arranged in this way, and the coordination number is indeed 6, and the same applies for the same coordination number is adopted by the large atoms which are in the close-packed array. But in this case, unlike the octahedral, unlike the FCC structure, here the red atom is surrounded by green atoms which are not in octahedron but trigonal prism. You see that this and these atoms lie above each other, and also this and this atom lie above each other, and also this one, and this one. Okay, so this is a shape of trigonal prism. The ratio of the coordination numbers is 6:6, which is equal to 1:1, applicable for octahedral positions, but the arrangement is different. The coordination polyhedron for the small atom and the large atom are different, octahedron and trigonal prism. Now, if we want to consider the structures as close-packed arrays of larger atoms, and the smaller atoms are occupying the tetrahedral or octahedral side, we must consider the atomic or ionic radii. That means the size of the individual atoms. And generally, a larger atom can be placed into a given interstitial site. I mean larger atoms than the optimum, the atom which perfectly matches this void or this hole. For tetrahedral, it would be the ratio between the small, the radii of the small and large atom would be 0.225. And for the octahedral, which corresponds also to square planar arrangement, it would be 0.414. So a larger cation can fit, can occupy the octahedral side compared to the tetrahedral one. But it can be larger, but never smaller. You can't place an atom in a tetrahedral position if its radius is smaller than that corresponding to this ratio. In such a case, we would have some local distortion of the coordination polyhedron. So some atoms would be approached, and some others would be displaced out from the central atom. So the symmetry would be lowered if the atom is if the atom was smaller compared to this optimal ratio. We could also consider the triangular side, which is in fact the side exactly between these three these three atoms. So and this triangular side is even smaller compared to tetrahedral side, which is slightly shifted above the trigonal side. So you see that for the triangular side, the ratio is even smaller. We could also have square antiprismatic or cubic arrangement, but this is not typical for the closest packing like HCP or CCP, but it is typical. The cubic arrangement or cubic coordination number is typical for the BCC structure. So if we substituted the atom in the BCC structure by another atom, we would require this this eightfold coordination number. Perhaps I didn't explicitly mention that in the BCC structure, the coordination number is 8, which means smaller compared to the HCP or CCP structure. But we have additional atoms here, which are at the distance of one lattice parameter, while the atoms in the corners are in the distance a times square root of 2/2, so 1/2 of the body diagonal, which is a closer distance compared to the other 6 atoms, which are in the centers of the neighboring unit cells. But even this distance can be considered as a bonding distance. So we have 8 atoms closer to the considered atom and 6 atoms in a larger distance. So the effective coordination number for BCC structure is something between 8 and 14. Okay. And the cubo-octahedral side is in fact a side inside the close-packed structure, hexagonal or cubic. So if we replace or substitute one atom by another one which has the comparable size, then the optimal ratio would be 1:1, where the atom which is substituted into the close-packed structure of another type of atoms is exactly of the same size as the original atomic size. As mentioned, for the octahedral and tetrahedral sites, we usually consider an array of ions of one type, and the other type of ions, usually cation, is placed into octahedral or tetrahedral site. So we have to consider the ionic radii, and there are several sets of ionic radii which have been published in the past. The first one was published by the founder of crystal chemistry, the Goldschmidt. Then it was slightly improved and extended by Linus Pauling, and the recent list of ionic radii has been published by Shannon and Previtt, and this is the most extended set, which also includes the dependence on the coordination number on the valency of a given atom or charge. So let's say for copper we have the ionic radii of copper for copper 1+ and copper 2+, and we have also their dependence on the coordination numbers. So they slightly depend on the environment in which the atom is positioned. And even more for transition metals, the ionic radius depends on the spin state. Usually the high spin state has a larger ionic radius compared to low spin state, because the electrons with the same spins correlate their motions such that they try to keep as far as possible from each other. So the atom is larger due to these electron-electron correlations with the same spin. Okay, now based on this concept of occupation of different sites in close-packed structures, we can derive a number of structure types. For instance, if we consider a close-packed array, in this case large cations and small anions enter all tetrahedral sites. So if all tetrahedral sites are occupied, so we have the occupation number of 1, the resulting stoichiometry is 2:1, because there is twice as many atoms in tetrahedral sites compared to the atoms in close-packed array. And the coordination numbers are in the reciprocal ratio or inverse ratio compared to stoichiometric coefficient. So the atom in close-packed array is coordinated by 8 atoms in tetrahedral positions, and indeed each atom in tetrahedral position is occupied or is coordinated by 4 atoms in the close-packed structure. So the coordination number for an atom whose stoichiometric coefficient is lower is higher. So calcium is occupied by 8 fluorine atoms, and fluorine is occupied by 4 calcium atoms. So the ratio or the fraction between these two is opposite. For a complete occupation of octahedral sites, we have the stoichiometry 1:1, and the ratio of coordination number is 6:6. In cubic close packing, it is octahedral for both types of atoms, while it is octahedral and trigonal prismatic for the atoms in octahedral positions and close-packed arranged atoms in hexagonal close packing. Then, as mentioned, it is impossible to occupy all tetrahedral sites in hexagonal close-packed array. So if we occupy only one half in an ordered manner, we obtain the wurtzite and sphalerite or zinc blend structures. So this corresponds to hexagonal close packing of sulfur atoms, and this corresponds to a cubic close packing, and one half of tetrahedral positions is occupied by zinc atoms. If we fill only 2/3 of octahedral sites in hexagonal close packing, we obtain the corundum structure. If one half of octahedral sites is occupied in a layered pattern, so one layer is completely occupied and the other one is empty, we obtain the cadmium iodide and cadmium chloride structures. If we arrange the octahedral sites occupied and unoccupied in a different pattern, we obtain the rutile and anatase structures, which are the polymorphs of titanium dioxide corresponding to hexagonal and cubic close packing. But for rutile, in both cases, in fact, due to arrangement of filled and empty tetrahedral sites, the resulting structure is not hexagonal or cubic, but tetragonal in both cases. And I will show how the distortion of the unit cell results in tetragonal symmetry. And here, if we occupy 1/3 of octahedral sites in HCP and CCP structure, we obtain the structures of bismuth iodide or chromium trichloride and so on. And now we would, I would show the respective structure types and discuss them in more detail. The first and the most famous structure type is the sodium chloride or rock salt structure types, where all octahedral sites are occupied. We have always, I will show the unit cell, single unit cell, and a more extended part of the crystal lattice. Here it is 2 unit cells in each direction, and then the arrangement of coordination polyhedra. You see that in rock salt structure type, there are octahedral sites occupied. So we have the atoms of close packing in the corners, and in the centers we have the smaller atoms in octahedral positions. And we see that the octahedra are edge shared in an NaCl type. The resulting space group is the same as for the simple FCC structure, and here the formula involves also the coordination numbers of both atoms. And this symbol was used in the past as a classification symbol for this different crystal structure types. Nowadays it's not so used so frequently. In fact, we have A, B, C symbols where A corresponds to an element, B for a binary compound with the ratio 1:1, and C corresponds to a binary compound with 1:2 ratio, and so on. D corresponds to ternary compounds and so on. And the number is just an index, so it has no special meaning. It is just a convention, or that B1 is the rock salt. Let's say A1 would be, I think, I don't know if cubic or hexagonal close packing corresponding to either copper or magnesium metal, which are the prototypes of these structure types. Okay. The rock salt structure type is adopted by many compounds of different types, not only the halides of alkali metals, but also oxides of alkaline earth metals like CaO or BaO or strontium oxide and so on. Also the binary monooxides of transition metals like MnO or iron oxide and so on. Also carbides and nitrides of many elements adopt the rock salt structure type. What more? Other there is an overview of structures which adopt this crystal structure types. Also the alkali metal hydrides, which are similar to halides, they are also ionic compounds. Also sulfides and selenides and other chalcogenides, and some intermetallic compounds or alloys. But we can also derive other structure type, but I must skip many slides. Here, we can place a molecule at the position where we had an anion originally. So instead of chloride anion in rock salt, we can place a molecule or a cluster, like in pyrite or iron disulfide. We have for an anion, we have a dimer S2,2- disulfide anions, and the disulfide anions are arranged in a zigzag pattern such that the resulting symmetry is still cubic. We have a cubic unit cell, but the space group is different. The symmetry is lowered, so we have no face centering, and we also lost some mirror planes. So this structure type is corresponds. It can be derived from rock salt structure type, but it is C type because the ratio of elements is 1:2, and so this is one example. And the second example is calcium dicarbide or acetylide, where the dicarbide anions, which are C2,2-, are arranged along or oriented along one crystallographic direction, and this lowers the symmetry. The resulting unit cell and the space group is tetragonal, because if we place all dimers along the C direction, then indeed the symmetry is lowered from cubic to tetragonal due to different spacing between the atoms. But even if we didn't change the lattice parameters and we oriented the dimers in a single direction, then the symmetry would be lowered from cubic to tetragonal, even if the C parameter was the same as the A and B parameter. But the symmetry would be lowered anyway, and perhaps you don't see the relation between the FCC structure or rock salt structure and this unit cell, and the relation is the following. If you have the cubic unit cell, and you have one type of atoms in corners and also in the center. This is what you have to fill in your exam tests. These sections which are perpendicular to a given crystallographic direction. So this section corresponds to the Z parameter equal 0 and 1, and we have another section for the Z coordinate equal to 1/2, and in this case we have the large atoms in the centers of the faces here, and the second type of atoms will be here. So we have the second type of atoms here, and here we are at the edges and in the center. And if these atoms are the dimers oriented perpendicular to this plane, then the unit cell would be this one. So it is the phase diagonal divided by 2, the new lattice parameter. So this is A tetragonal, and this is A cubic, and A tetragonal is A cubic times square root of 2 over 2. And the C parameter would be the same, or not the same compared to the ideal cubic lattice. It would be elongated because of placing this dimer to here. Okay, so this is the calcium dicarbide. There are also other structures or compounds crystallizing or calcium dicarbide. It is lanthanide dicarbide, which is surprising because the lanthanum is 3+, and the acetylide or dicarbide is 2-, so there must be some compensating electrons. So this structure is in fact metallic due to different charges here and here. So if this is 3+, and you would consider this as 2-, then it must be, there must be some electrons which lower this charge, which are likely delocalized like in a metal. So this is one type of compounds adopting this structure, but also, for instance, barium peroxide or strontium peroxide have the same structure as calcium dicarbide, or some superoxides like potassium superoxide have also this structure. Okay, let's come back to this is rock salt. And now if we fill all tetrahedral sides, we obtain the fluoride or calcium fluoride structure, which again has Fm3m symmetry. The coordination numbers are 8 and 4, cubic and tetrahedral. You see the unit cell, the structure consisting of tetrahedra which share the edges, and the whole structure here. And this is the fluoride type, where the calcium or larger cations form the close packed structure and the smaller anions enter the tetrahedral sides. This structure type is adopted by some actinide oxides like UO2 or plutonium O2, and some other oxides like high temperature form of zirconium oxide or hafnium oxide. There are also some halides like cadmium fluoride or strontium chloride. All these structures adopt calcium fluoride, cadmium fluoride or strontium chloride and so on. But there is also the so-called anti-fluoride structure, which is a more frequent case where large anion forms an array of close-packed atoms and smaller cation like lithium enters the tetrahedral interstitial sites 2:1. The similar structure is adopted by some other oxide like sodium oxide or also chalcogenides like sulfides and selenides of alkaline metals. Also, the lanthanum oxide fluorides or oxide halides like LNOF, lanthanum or other lanthanides. LN stands for a general lanthanide. Oxide fluoride have this structure like fluoride, but in this case these atoms are oxide and fluoride and they are ordered. So we have 2 oxides and 2 fluorides and 2 fluorides and 2 oxides. Okay, then I would, together with this, I would discuss also the pyrochlore structure, which can be derived from fluoride structure. In fluoride, we have the stoichiometry AX2 generally, but if we multiply the units, this formula unit by 4, which means you have to create a supercell. In fact, the supercell contains 8 unit cells of the original fluoride structure. You obtain the stoichiometry A4X8, and now you replace 2 out of 4 atoms A by another type of atoms, like niobium is replaced by calcium or something like that. And they are ordered, so they are not randomly distributed, even if they occupy the same type of positions, but they are not randomly distributed, but they are ordered. And then we leave out a single atom, so we create an oxygen or anion vacancy on this sublattice. So we don't have 8, but only 7 atoms. So the resulting stoichiometry is 227, and the mineral pyrochlore would be, for instance, calcium 2, niobium 207. But if calcium is replaced by sodium, we must satisfy the charge balance. So if we decrease the cation side here, we must decrease the anion charge as well. So instead of having oxide anion, we have OH minus or F minus. But this is already a so-called solid solution, so we introduce the substitutional defects, and I'm going to talk about the defects later on. So here there is a random distribution of sodium and calcium atoms on this sublattice. And the resulting ideal pyrochlore structure looks like that, but as I mentioned, it can be derived from the fluoride structure. Also, here, we can also place some clusters like coordination complexes. So for instance, the compound K2 PTF6 can be viewed as a close-packed array of these clusters or complexes, and the cations occupy the tetrahedral sites in this close-packed array, and so on. Okay. Now the sphalerite, or in English it is rather zinc blende structure, zinc blende. We have only 1/2 of tetrahedral positions occupied, like here. So 2 atoms in one layer on one phase diagonal, and the other 2 atoms in the next layer on the other phase diagonal. Tetrahedral arrangement. Now also this atom, the green atoms, are also tetrahedrally coordinated. And if we unify these 2 atoms, or if we consider a single type of atom here and here, we would obtain a diamond structure, which is present in diamond high pressure form of carbon, but also in silicon, for instance. The zinc blende or sphalerite structure is adopted by the compounds which are isoelectronic with carbon on silicon. That means each atom contain, or there are 4 electrons per a single atom. So in diamond structure, where the red and green atoms are the same, we have each atom contributing by 4 electrons, so 8 electrons per this couple. And in zinc sulfide, it is the same. These compounds are sometimes referred to as A2B6, because the anion, the B atom, like sulfur or other chalcogen, has 6 valence electrons, while zinc contributes by 2 electrons, and 2 and 6 is 8. Which is the same as for diamond or silicon. Or there are also A3B5 compounds of this type. So if this is an element of the 3rd main group and 5th main group, or 13 and 15 group, like gallium or indium, and here nitrogen or arsenic or something like that, we have again an isoelectronic structure. So gallium arsenide and others, A3B5 compounds, adopt this zinc blende structure. And we could also interpret the structure of silicon dioxide in high temperature form, which is called cristobalite, using the sphalerite or zinc blende structure. Namely, if we consider the silicon atoms here on green positions, and we place the cluster of SiO4, that means silicon, and 4 atoms of oxygen in tetrahedral arrangement, such that the oxygen atoms for bridges on each silicon pair. So if you consider the oxygen atom here, 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 and here, you would have a doubled number of oxygen atoms, and the resulting stoichiometry would be SiO2. But it is a high temperature form of silicon dioxide. Then cesium chloride structure is also very frequent, or many other structures can be derived from it. It is typical by relatively high coordination number, so the ionic compounds with large cation crystallize in this structure type, like cesium chloride. But we could also place a molecular cation on the large cation position. Like ammonium chloride contains the ammonium cation here, and at lower temperatures it is fixed in a certain arrangement, but at higher temperatures the NH4 plus molecule can rotate, but it still fills this void or this cubic position. We can also interpret the structure of calcium hexaboride, which is hexaboride, by considering the calcium atoms as green ones, and we place the octahedron with no atom inside the octahedron, an octahedron of B6 boron atoms inside this unit cell. So we obtain this structure, and also the cuprous oxide, copper-2O, can be considered as a cubic array of oxygen atoms. So let's consider the oxygen atoms on green positions, and then in the center you put oxygen atom, but in fact a cluster of oxygen and 4 copper atoms. So you put Cu4O cluster in the center of the unit cell, and each copper atom, it is a tetrahedral unit with oxygen atom in the center, and each copper atom is coordinated linearly in dumbbell coordination between this and this oxygen atom. So we have one copper atom here, another copper atom here, and the third one is between this and this atom, and the fourth one between this pair of oxygen atoms. So this is the structure of so-called cuprite or copper-2 oxide. Now, as already mentioned in the overview table, if you use the hexagonal close packing and you put the zinc of sulfur atoms, and you put the zinc in 1/2 of tetrahedral positions, you obtain the other polymorphic form of the zinc sulfide, which is called wurtzite. So you see that we have green sulfur atoms and zinc atoms are in tetrahedral positions. You also can see that unlike the complete filling of tetrahedral positions in calcium fluoride, where we have the edge-sharing tetrahedra, here the tetrahedra are corner-shared. The symmetry is hexagonal, P6,3MC. The structure type is B4. And again, the A3B5 or A2B6 compounds can adopt this structure. For instance, for silicon carbide, which is also isoelectronic, silicon carbide, we have both sphalerite or zinc blende and wurtzite polymorphs, but for silicon carbide we have also the more complex patterns where zinc blende and wurtzite structures are stacked in a certain order along the C direction. So and this polymorphism is called polytypism, that the hexagonal and cubic patterns are stacked in an ordered manner along the C direction. Now, if you fill all octahedral positions in hexagonal close-packed array, you obtain the nickeline or nickel arsenide type. So again, we have the edge-shared octahedra. We also know that the opposite coordination is trigonal prismatic. And this structure type is mostly observed for some intermetallic compounds. It is not as frequent as the other types which have been already discussed, but some intermetallic compounds can adopt this structure. But we can also derive the rutile or titanium dioxide structure by considering by leaving out 1/2 of octahedral positions. So we have only 1/2 of octahedral positions occupied in this pattern. So 1 full, 1 empty, 1 full, 1 empty, and here empty, full, and so on. And this would be still hexagonal, but if we slightly distort these octahedra, we obtain the tetragonal unit cell with the A and B parameters equal, and the titanium atoms are in the corners and in the center. But interestingly, the unit cell is not I, that means body centered, but it is primitive. And the reason is that the oxygen atoms, which are here on faces and here in trigonal arrangement, they don't fulfill this condition of body centering, and that's why the overall symmetry, translational symmetry, is primitive. So as you can see here, the octahedra TiO6 form these ribbons or chains with edge sharing here, but these ribbons or chains are interconnected by corners. So this is the resulting structure of rutile, which is adopted also by other transition metal oxides like manganese dioxide or some fluorides and so on, magnesium difluoride, or a distorted structure of this type is also observed for tin dioxide and lead dioxide, so SnO2, or a distorted form of this is PbO2, and so on. So rutile is a quite frequent structure type. Now, corundum structure is obtained if we occupy just 2/3 of octahedral positions. So one layer, one close-packed layer, or in fact 2 layers of close-packed atoms with 2/3 of octahedral positions occupied are shown here. So you see that 2 positions are occupied, 1 is empty, 2 are occupied, 1 is empty. And this forms this hexagonal pattern. Well, the overall symmetry is rhombohedral, but as we know, we can use the hexagonal setting for rhombohedral unit cell. But the empty sides and filled sides are different in different layers. So you see the stacking pattern along the C direction. So in fact, we obtain a very rigid structure, very stable structure, which is adopted by aluminum oxide, but also chromium sesquioxide. In a distorted form, also the iron sesquioxide and many others. occupying 1/2 of octahedral sites, but in a layered pattern such that one layer is completely occupied and another layer, or the octahedral sites between two layers are either completely occupied or completely empty. And if we start from the cubic close packing of, let's say, halide ions, and we place cadmium atoms here, and we leave these two layers empty, and again cadmium atoms and empty double layer, we obtain the cadmium chloride structure type, and the resulting symmetry is not cubic anymore, because we have only van der Waals interactions between these individual blocks, and this imposes an extension along this C direction of the original hexagonal close packing. So the resulting, or in this case, cubic close packing. So this is the direction of stacking along this direction, but due to weak interactions between those blocks, the resulting cell is not cubic but rhombohedrali distorted. And if we start from hexagonal close packing, we obtain the cadmium iodide structure type, which is very similar to this one, but only the layers are in the order AB, AB, while here we have ABC, ABC, and so on. There are many chalcogenides like molybdenum or tungsten dichalcogenides. So the structures like molybdenum disulfide or tungsten diselenide or rhenium disulfide, and many others adopt these one of these crystal structure types, either cadmium iodide or cadmium chloride. In fact, in molybdenum disulfide we have also another also this similar type of layers, but molybdenum is in trigonal prismatic coordination. This is the third type or polymorphic form of molybdenum disulfide, where molybdenum sits in a trigonal prismatic coordination. And now I would briefly outline the several types of ternary compounds. A perovskite is quite typical for many ternary oxides, but also some halides. And here we have to start with the close-packed array of one type of atoms, but let's say anions, which are green here, like oxide anions are in green. But in this close-packed array, we replace a part of anions by a large cation, like calcium. So if we start from the unit cell, which contains 4 anions, and we replace one anion by a large cation, so we have AX3, which is shown, I think here it is most appropriately depicted. This is in fact the FCC structure consisting of green and yellow atoms altogether, and then we fill 1/4 of octahedral position. So as you can see here, we have atoms in octahedral positions here, for instance, but we don't have the atoms here and also on these edges. This and this unit cell is just shifted by 1/2 of 1 lattice parameter. So here we have this atom in the center of the unit cell, this large cation, and here it is in the center of two faces. And here the small cations which fill the octahedral sites are on edges, while here they are on in the corners. And as you can see here, the structure can be interpreted as an array of octahedra which are corner shared, and the large cations are in between. So we can have a divalent large cation and a tetravalent small cation, but we can also have both cations trivalent, like lanthanum, manganese, O3, or gadolinium, iron, O3, where we have trivalent small cation and trivalent large cation. So this is a perovskite structure. It is primitive unit cell, cubic 1, PM3M. Yeah. And the small cations are 6-fold coordinated, while the anions are only 2-fold coordinated. This anion is coordinated by 2 small cations. But indeed, there is this large cation is 12-fold coordinated. 4 atoms here, 4 atoms here, and 4 atoms here. Yeah, and the other ternary oxide, which has quite frequently occurring structure, is the spinel. Here we have both cations are relatively small, but one is either even smaller compared to the other one, or it prefers the tetrahedral coordination due to electronic configuration. For instance, the atoms which have the configuration D5, like iron 3+, or D10, like zinc 2+, but also in some cases D6, like D7. D7, like cobalt 2+. In all cases, in tetrahedral positions, we have 2 levels and 3 levels due to crystal field splitting. And we would have, for D5, it would be this configuration. So we have an orbital singlet. For zinc, it would be completely occupied. And for cobalt 7, D7, it would be this electron configuration, which is also an orbital singlet, and it is relatively stable. So there are some atoms which prefer the tetrahedral configuration due to electron configuration. And in the spinel structure, we have a close-packed array of anions, like oxygen atoms, oxide anions, and 1/2 of octahedral sites is occupied, and 1/8, so 1/8 tetrahedral site is occupied, because the tetrahedral positions are doubled compared to the atoms in close packing. So if we want to create a stoichiometry 1 to 4, we must occupy only 1/8 of the tetrahedral site. If you look at this unit cell, where the atoms in tetrahedral positions are in the corners, it is a cubic unit cell with FD3M symmetry. So if we place the atoms in the corners, then you see that there are additional atoms here and here, and here and here, which corresponds to diamond lattice. This is a diamond lattice of atoms which occupy the tetrahedral sites. And the structure can be also interpreted as consisting of this type of octants. So we have one octant occupied by atoms in octahedral positions. So the purple atoms are in octahedral positions, and in the octant next to it there is only tetrahedral position occupied. And we have and these two octants are placed in this direction, but in the other two octants which are behind have this arrangement switched. So octahedral sites are occupied here and tetrahedral site is occupied here. And again, above and behind, there is always an alternative arrangement of these octants. And as concerns the interpretation of the structure in terms of polyhedra, we have these ribbons of or chains of octahedra which are edge shared, and they are interconnected by tetrahedral sites which are in green here. And we have two types of spinels. One is the normal spinel, like the MgAl2O4, but even this spinel, which is a mineral, if you when you find it in nature, sometimes the magnesium and aluminium are partly interchanged, so they form the solid solution or substitutional defects. But there are some spinels which are completely inverse, where one atom B is in tetrahedral position, and we have a mixture of atoms A and B in octahedral position. So if this is tetrahedral and this is octahedral, we have this form and O4 or X4, and this is observed, for instance, for iron oxide spinel Fe3O4, where we have iron 3+, which prefers the tetrahedral coordination, but there must be two iron 3+ because of maintaining the charge neutrality. So here we must have one atom Fe2 and two atom Fe3O4, but here the distribution is that all iron atoms with 3+ occupy the tetrahedral positions, and we have a mixture of 2+ and 3+ in octahedral positions. And this is referred to as inverse spinel. Okay. While the normal spinel is, for instance, manganese 3O4, where manganese 2+ is D5, so it prefers the tetrahedral position, and manganese 3+ prefers the octahedral position, even if it is tetragonally distorted. So it is this spinel is not cubic but tetragonal due to Jahn-Teller effect of manganese 3+, which is D4 configuration. Yeah, I mentioned already pyrochlore, structure types based on sodium chloride, and then some examples of low-dimensional structures which can be derived from close packing. The chain silicane structure like diopside, which is calcium magnesium disilicate, has this zigzag arrangement of silicon O4 tetrahedra along one crystallographic direction. In silicates, which are oxides, the tetrahedra SiO4 are always corner shared, There is one exception in chalcogenides. The silicon disulfide has edge-shared tetrahedra, but it never occurs in oxides. In oxides, in normal silicates, we always have corner-shared structures. Then some examples of layered structures like hexagonal graphite or black phosphorus, which has a similar but buckled or buckled structure. Then layered silicates like kaolinite, which involves the layers of corner-shared tetrahedra, which has the stoichiometry Si4O10. And these layers are similar to cadmium iodide and or cadmium chloride, and they contain the aluminium occupied by hydroxide groups. So these blocks of hexagonal octahedrally coordinated aluminium and tetrahedrally coordinated silicon are stacked along one crystallographic direction. But we can also observe the 3D networks. We know that diamond structure can be derived from sphalerite or zinc blende structure, but for instance, the silicate like garnet, magnesium 3, aluminium 2, and SiO4 3 times, yielding the total stoichiometry Mg3. Sorry. Al2 Si3 O12, but sometimes in some garnets this and this side are formed by the same atom. So we have, for instance, yttrium, here is 3, yttrium aluminium garnet, or yttrium iron garnet, where aluminium and iron occupy both tetrahedral and octahedral positions, while this higher coordination number polyhedron, a dodecahedron, is occupied by a lanthanide or yttrium as well. These garnets are very important as hosting some lanthanides or rare earth with important optical properties or magneto-optical applications. And so also 3D networks are observed for quartz and tridymite. And we mentioned cristobalite, which is the high temperature form of SiO2. For quartz, we can start from, as with the cristobalite, where we started from zinc blende structure, and we replaced one silicon atom by SiO4 units. If we do the same procedure for the hexagonal structure of wurtzite, and we replace one silicon atom by SiO4 units, we would obtain the quartz structure. So, and last point is just quickly, the real crystals always contain some defects, which can be natural, but we can also artificially introduce the defects and tune the stoichiometry and tune the properties by introducing the defects. We can classify the defects as point defects, line like dislocations, surface defects like phase boundaries or grain boundaries, or stacking faults where different order of layers or a specific order of layers is disrupted, and we have the so-called stacking faults, or bulk defects like inclusions or pores. But for crystal chemistry, the point defects are relevant, and we can have a vacancy. If it is a defect, it is either isolated, or if there are more defects of such type, they are randomly distributed over a given sublattice. So vacancies are one type of point defects. Substitutional atom, interstitial atom can be regarded as an atom occupying an originally vacant position, regular position, but originally vacant. And then we have a combination of different types of defects, but Schottky and Frenkel defects are more typical for binary compounds, like in ionic crystals. The Schottky defect is a vacancy on cation side occupied by compensated by a vacancy on anion side, and here Frenkel defect is a vacancy on one side compensated by an interstitial, that means an irregular position on another side. So a combination of interstitial and vacancy is called Frenkel defect. In charge structures, there must be always a compensation, a charge compensation, and I will talk about this in the last presentation devoted by electronic structure or band structure. Sometimes a charge defect can be compensated by electrons or holes in a given band structure, but sometimes the electron or hole is associated with a certain site, and in that case we speak about the ion of different valency. So let's say here, if we have the lanthanum manganese trioxide and we make a substitution defect on large cation sublattice, and we substitute lanthanum, let's say by strontium, and lanthanum is 3+ and strontium is 2+, then in order to preserve the charge balance, we must have manganese 3+ 1- X and manganese 4+ X. So this lower valency of strontium as a substitution defect is compensated by an increase of valency of manganese on the small cation side. So this is one type of compensation. In real ionic crystals like sodium chloride, if we remove one atom, such as an anion, we have a missing negative charge, and this is compensated by an electron, but this electron is not moving freely, but it is attached or attached to this vacant site. This is called F center. But for instance, in semiconductors like silicon, if we replace silicon atom by phosphorus, 1- X, phosphorus X, phosphorus has more electrons than silicon, and this additional electron, we have the band structure with the valence band and conduction band. This additional electron, it occupies the localized energy levels just below the conduction band, which means that it is attached to this substitutional defect. So we have the silicon lattice, and here is, for instance, phosphorus and silicon, and this electron moves somewhere around this substitutional defect, and it is localized. But once the temperature increased, it can be excited into this valence band, and it can freely move all over the crystal. So it becomes the part of the electronic structure of the parent silicon structure. Or if we put boron, which contains lower number of electrons, 3 compared to 4, we create the empty sites which are at low temperatures attached to boron atoms, so they are localized, but at higher temperatures the electrons can be excited here, and the holes in this valence band can move all over the crystal. So this is another type of defects which can which is observed in semiconductors, and the compensation of defects by some charged species, electrons, holes, or ions with different valency and so on.